Okay, so this video is going to be on the acids and bases, and in particular it's going to be on the acid dissociation constant Ka. So we should already know that weak acids only partially dissociate into their ions in solution, and an expression for this we should also already know, I guess, is Ha dissociates in an equilibrium reaction to H plus A minus. As with any equilibrium reactions then, we can write a Kc type expression for this, and for weak acids, instead of using Kc, we use the constant Ka. This K expression is therefore products over reactants, so it's Ka equals H plus times by A minus, both in square brackets to show concentrations, all divided by Ha, again in square brackets to show it's the concentration of. So then using this though, for weak acids in aqueous solution, we can further simplify this equation, and we can simplify it into being Ka equals H plus squared over Ha. And the reason we can do this is because weak acids only partially dissociate in solution. So from this we can assume that they dissociate evenly into their ions. H plus will equal A minus in that instance. And this is similar then to the principle we applied for deriving the Kw equation for the water dissociation, because that's also weakly dissociated, and we can assume that H plus equals OH minus. So it's the same principle there. And I've done an example calculation for a weak acid, and, well, I'll read out. So, calculate the pH of a 0.10 mole per decimeter cubed solution of methanoic acid, where the Ka for this is 3.6 times 10 to the minus 4 moles per decimeter cubed. So this is a standard weak acid in aqueous solution, so we can assume that H plus equals A minus. So doing this, and then we can write the equation as 3.6 times 10 to the minus 4, subbing in our Ka value, equals H plus squared all over Ha. We can then rearrange for H plus, and this will give us H plus equals the square root of 3.6 times 10 to the minus 4 times by 0.10. And you could have subbed in your concentration of acid. I don't know why I didn't do that there. You should do that. But anyway, doing this second step gives us a hydrogen concentration of 6.0 times 10 to the minus 3 moles per decimeter cubed. The final step of this is quite easy. We just use the standard pH equation, and that is minus log base 10 of our hydrogen concentration, so 6 times 10 to the minus 3, and if you plug that into your calculator, you're going to get 2.22 for your pH. Smiley faces, because it's quite easy. So another thing we need to know then is pKa, and we need to know that this can be used instead of Ka, and this is because Ka can be very varied. So due to this, we use pKa for the same reason we use a pH scale instead of just the hydrogen concentrations. So if you think about it, you don't want to be dealing with concentrations of 6 times 10 to the minus 3 when you can have just pH 2.22. Similarly then, we don't want a Ka of 3.6 times 10 to the minus 4, we'd rather have a much nicer number. So anyway, pKa expression is pKa equals minus log Ka, and I just thought it'd be useful for your understanding to know this, but whenever you see a P, it means minus log, so pH is minus log hydrogen concentration, and pKa is minus log Ka, so hopefully you'll see why we keep writing minus log. So to work backwards from this to get Ka from pKa, we do the inverse log, which is 10 to the power of the minus of the pKa. So to get that 10 to the power, we just press shift and log on your calculator, and, well, a Casio will come up with the inverse of log. So there's another way though of calculating pH, and this is using pKa, and the equation for this is pH equals half pKa minus half of the log of whatever the concentration of the acid is. So using the same example I used for the previous equation, which was the h plus squared all over HA, you can see that, again, calculate the pH of a 0.10 mole per decimeter cubed solution of methanoic acid, where Ka is 3.6 times 10 to the minus 4 moles per decimeter cubed. What we can do for this is we can get the pKa value from the Ka. pKa is minus log then of 3.6 times 10 to the minus 4, giving us a pKa value of 3.44. If you just plug them into your calculator, you will see how I got that value. Then we just use the pH equation regarding pKa. So obviously that's the half pKa, so 3.44 divided by 2. Take away half log of the concentration of the acid, so log base 10 square brackets 0.10, all divided by 2, and this again gives us a pH of 2.22. So this method, one, can be used to check your answer if you decided to use this. 2, I find this method quicker and pretty much easier. And 3, if you're not given Ka and you are given pKa, well then you know what you can do. So finally, to end this video, we just need to know how the Ka values and pKa values correlate in terms of the acid. So for a strong acid, we will have a large Ka value but a small pKa value. For weak acid, it'll just be the inverse of this. So we'll have a small Ka value and a large pKa value. And that's all you really need to know for the Ka equations. You will see them again in buffers, but we'll get to that when we get to it.